Yeah, that's good.
Okay, so thank you very much for having me, and I'm also feel very pleased to share my recent results and to also introduce my research work about the residence time. So my topic is about the acceleration of the hydrological cycle and the global warming. So in this talk, I will introduce the regional climate model based the water tracking approach, especially for estimating the residence time of water in the atmosphere. Yes, about us, yes, now I am in the Germany, the south part of the Germany. And the name is Garmisch-Partenkirchen. So our group is the focus on the regional climate hydrology and lead by Professor Mann. And for our talk this talk is mainly about the atmospheric water residence time. Why we focus on this is because the residence time of water in the atmosphere is an indicator of the speed of the water cycle. So, but the thing is, if we focus on under global warming, so this also will change the speed of the water cycle. And if we focus on the land atmosphere, land surface, which is evaporation or transpiration, this is different land surface characteristics. This will also affect the water, the age of the water in the atmosphere. So this is especially for the regional scale. What we saw this is the global water cycle. We have evapotranspiration from the ocean and also from the land surface. And we get precipitation over the ocean and land. So in general, what goes up must come down. And the condition of global warming, now the situation is the global warming is accelerating the global water cycle. But if we focus on the regional scale, this is largely unknown. So my research question is about, is the water cycle regionally accelerating or decelerating and the global warming? And what is the tipping point between the accelerating or deceleration? So to answer this question, we need to derive the speed of the water cycle. And by comparing this speed, so we can quantitatively estimate or investigate the changes of the water cycle. So for this, we need to develop the new method, which we called Wolf Age model. And this method is a regional climate model-based method. And in the method, we implemented an age-weighted regional water tagging approach. So for WRF, I think most of them, of us, we are familiar with, it simulates the land surface processes, and also it simulates the atmosphere part of the water cycle and energy cycle. So we use this model and to implement it an age-weighted regional water approach. And so with this implementation, we can derive the age of water in the atmosphere. And the concept of this age-weighted regional water tagging approach is, first, we need to define a mask in the model to track the evaporated water from the specific region. And then we follow the atmospheric transport processes and also goes to the phase change until it falls as the precipitation over the land. This we follow the atmospheric pathways. And by tracking this, we track the quantity of the the evapotranspirated water. At the same time, we implemented the age information that allows us to derive the residence time of water through the each processes quantitatively and at the same time. And my study region is the Southeast China, because this is the region has highly complex mountainous region. And for this region, it has controlled by the complex monsoon system. This means in winter, we have the winter monsoon from North Siberia, and in summer, we have the monsoon from the ocean. So with this monsoon system, we need the advanced method to understand how the water cycle or residence time will be changed. And my study region is, or the moisture source region is the Poyang Lake region in China. And for this catchment is around 2.5 times larger than the state of Bayern here. And for this region, it contains the largest freshwater lake in the country. So this means for this basin, we have the land surface or the forest, and we also have a large amount of the open water in the basin. So we applied this model for this area with the two domains setup, and we use the MPI RCP 8.5 scenario as a forething to drive the model. And for this, we choose two 10-year simulation. One is the historical period, is 1980s, and another is around 2014, 40s for these 10 years. And for the following, I will compare these two 10-year simulations to see how the water cycle will accelerate. And to demonstrate how the model or the algorithm is we track the evapotranspiration from the basin. And you will see how the hourly changes of the tagged water in the atmosphere will changes under the impact of the wind system. And this part is the residence time of the tagged water vapor. You will see with the model iteration and the residence time of the water will changes also. And if we get the larger amount of the evapotranspiration from the source region, the residence time here, like over the lake, becomes shorter. And when this moisture moves to the moisture source area, then the age of moisture will increase. So this is generally how this residence time, this method can provide the information for us. So what I would like to summarize is for moisture or the age of the water in the atmosphere, two factors can control this. One is the moisture source, and also the quantity, how the existing tagged moisture in the atmosphere. And another point is what is the atmospheric transport condition like winds. This will also impact the residence time of water. And since we apply this model for historical period and also for future period, so we can see under the warming condition, the air temperature will increase by around 2 degrees, and also the evaporation increase around 2%, but under this RCP 8.5, the precipitation decreases significantly. So this is the climate change, regional climate change condition. But under this condition, how the residence time, how the water cycle will changes. Then we show that this is a historical period of the residence time for tagged weeper. And for this is around 40 hours over the basin. But for future period, the residence time of the water vapor will decrease by around 1.8 hours. So when we think about the cloud formation, the residence time decrease around 1.7 hours. This means the water for water vapor and clouds is accelerated. But if we look at the residence time of tagged precipitation over the land surface, this is residence time increases, which means the age of water over the land becomes longer under the warming condition. So to understand why the clouds has less or younger age in the future, but for the precipitation has longer age in the future, we implemented an online budget analysis for age-weighted tagged water. So for this, the basic concept is we want to compute the physical and also the dynamical tendencies of the model iteration time. So this is the moisture tendency equation in the model. So it generally consists of the horizontal transport and the vertical transport, phase change, and fallout. This is how the model simulates the water. And we implemented this for age-weighted tagged moisture, which means in the model, we have two sets of equations. One is for tagged water, and one is for age-weighted tagged water. So with these two kind of implementation, we can derive a prognostic equation of the atmospheric residence time, and to understand how the processes or how to decompose the changes of the atmospheric residence time. And this means from the moisture transport to phase change to fallout, and also until it precipitates in the land at the land surface as precipitation. So this equation for different processes, the different moisture species are involved. So I will introduce you the details, what this meaning. Like for water vapor, we found it accelerate. But for water vapor, is most of the dominant factors is the transport. So this means this gives us the information that in the future that the transport processes increases so that the age of the water vapor decreases. But when we come into the phase change processes, it consists of the cloud water and the cloud ice. This part is the non-precipitating moisture species. And for this blue dashed part, the rainwater and the snowflakes, these are the precipitating processes. That means only this part of the moisture species can force out onto the land surface and forms the precipitation over the land. And by looking at the warming-induced changes of the residence time from transport to phase change to fallout and precipitation, we see that here from phase change to precipitate, the falling out is the tipping point, which means from the falling out processes, the age of the water cycle becomes slower. So with this equation implementation, we found that the warming-induced increases in the age of tagged water of the land is partly attributed to the slower fallout of the precipitating moisture components in this part. And this is about the warming induced changes in the residence time of water. And now we are coming to the evapotranspiration over the land surface. Since evaporation and transpiration, these are two different processes. What I showed you before is we only track the evapotranspiration. And now, since in the model, we can differentiate the evaporation and the transpiration. So we can also track evaporation and transpiration separately to know how the evaporated water and the transpired water, how they will cycle in the atmosphere. So we applied this method to track only this small area for the year of 2005 to see how the changes of evaporation and the transpiration. And this is the total tagged moisture, the residence time. And the upper part is the residence time for the moisture coming from the evaporation. And the lower part is the age of moisture contributed by the transpiration. We see that for the total moisture, it reflects the monsoon system, but we don't see so much difference for this evaporation and the transpiration. But when we come into the clouds, which here is condensed tagged moisture, we found that for the evaporation, it contributes to the cloud formation much faster than the transpired water. And by looking at the age of the tagged precipitation contributed by the evaporation and also by the transpiration, we also see that for the transpiration, the transpired water has longer residence time until it reaches as a land surface as precipitation than the evaporated water. This gives us the information that for transpired water and for evaporated water, they have different residence time in the atmospheric water cycle. So here I show the spatial pattern, how the difference of the transpired water, the age of transpired water and also the age of the evaporated water. But if we look at the profiles in the atmosphere, we find that for the water vapor, the evaporated water has shorter residence time in the lower atmosphere, but the transpired water has shorter water residence time in the higher upper level of the atmosphere. But when we come into the condensed tagged moisture, which is clouds, it says that always the transpired water has longer residence time than the directly evaporated water. So this gives us the information that the transpired water and evaporated water has different fate in the atmosphere. So for this talk, I introduce a new method or the new model which allows us to derive the residence time of water by additional accounting for physics and also the dynamics processes. And I also show that under the global warming, on the regional scale, the water cycle for the atmospheric moisture will accelerate, but for the precipitation will decelerate. This is because we have less precipitation over the land. And the tipping point is the cloud formation and also the precipitating processes. And from the land surface part, the transpired water and evaporated water has different fate in the atmosphere. And our conclusion is with this model, we can investigate the water cycle, especially the residence time at a regional scale and in more details. And we can also quantify how the changes of transpired water or evaporated water in the atmosphere separately. And we can also apply this method under the future scenario conditions. I think for all this is from these two manuscripts or from these two publications. With this, I would like to thank you very much for your attentions. Yeah.
Thank you so much. Let's see if we have some questions.
May I ask a question here?
Yes, please.
Yeah, please.
Yeah, a very interesting topic. And my question is that, did you ever try this method in other region or basins over the world? Because I think maybe the resident time will have a different, will be different in various regions over the world.
Yeah, for this method, now I apply this method to this part, the ocean, to track the contribution of ocean and to the tropical cyclone induced precipitation. And we investigate how this ocean part will contribute to the tropical cyclone induced precipitation. So my answer is yes, we apply this method for the ocean area now. But around the world, we didn't try this, another region.
Okay, thank you. Thank you.
Okay, thank you. I think any other question as well?
Yeah, my question will be very short. So according to your conclusion, you mentioned that because of precipitation is projected to decrease in your future scenario, then you found a deceleration of the tagged precipitation. So are you trying to insinuate the relationship that, okay, so if precipitation is going to decrease, then the water cycle is going to decelerate? How do you explain the relationship? I mean, if, for example, if future precipitation is going to increase, do you think the water cycle for the tagged precipitation is going to accelerate? So I'm just wondering the relationship between the two.
Yes, I think this is a good point that we found the deceleration here, and especially for the precipitation, because in general we thought that under the global warming and we have the atmosphere will have a higher water holding capacity, and then it will have more precipitation over the land. This is on the global scale, it's valid, but on the regional scale, we have drought that we have the warming condition, but under this warming condition, this is not suitable for cloud formation or for the precipitation processes, because the lift condensation level becomes higher and is not suitable for precipitating these processes. That's why you get less precipitation over the land surface. And under this condition, the falling down of the moisture has longer time than the traditional one. But if we looking at the heavy events like the typhoon cases, and this I would assume that under the warming condition, the tropical cyclone, this specific case, we will have the accelerated precipitation over the land because we have a lot of moisture. And this signal, the precipitation signal, is quite strong.
So you mean that it still depends on the weather system, right? So future, if
Yes, yes,
talking about
it's still,
there will be another story.
yes.
Before. And in your case, you just consider precipitation, right? I mean, you didn't separate whether there will be a tropical cyclone days.
For this, yes, for this study, I only show then the RCP 8.5, these extreme cases, how
extreme cases.
Yes, how this residence time of water will change under this condition. But we found that this is drought conditions. So with this condition, the residence time is longer for precipitation. But now currently I'm doing the tropical cyclone simulations. And we will try to simulate this event. And we will also apply it for the pseudo global warming, this strategy or approach to see if the ocean, the evaporation from the ocean part will have shorter or accelerated water cycle under the pseudo global warming, if this is really valid or not. But I assume this is valid under this condition.
Okay, thank you.
Thank you, Jianhui. Yeah, I think it will be very interesting to apply your method on different regions as well to see in how far you can generalize these results. But thanks a lot for showing this and sharing this with us.
Yeah.
If there are any more questions for Jianhui, please reach out to him personally or